Hey everyone, we're supposed to thrive and survive. This is going to be one of my most important videos I have ever made to date. At least for me it is. This hopefully will put to rest the question of gravity and density and different things like that. I've never seen a video that really explains how density and gravity are different and why I believe that gravity is just, like Newton himself didn't like the concept really, and thought it was just nothing more than what it is, a theory without proof. And what we can show here, I think, is with a question that was asked on this video here by Awake Souls. I'm going to try to remember to put the link down below, but if I don't, it's Awake Souls, 2 words. You can see that down here in the bottom left. Flat Earth river proof. Now, he does an excellent job not only at showing this is his #1 proof that he knows that the Earth is flat, but it also raised a question by a Flat Earth non-believer who claims he's banned from my channel. Maybe he is. I don't remember him at all, and I'm not the only one that has the ability to ban people from my channel. If there's certain people I have given that access to, and if they don't like what someone has written, they can ban them. So in any case, a question probably to try to foil this person, although I don't want to speak for the person, I don't want to know that for sure, but you can make up your own mind if you go to his channel and see what he has. But in any case, I don't want to leave anything untouched here. A lot of people who say, you know, well, if we live on a flat Earth, how come we can't see the Rocky Mountains and, you know, from New York and such and such, or see Tokyo and things like that. Here we have a river emptying into, I don't know what this is, a bay, a lake, an ocean, and we see here that there is a mountain range in the distance, and look how, even on a crisp day close, that whatever the distance of these mountains is, it's very hazy and blurry, and you cannot see it clearly against its background. It looks like there's more mountains over here, but I honestly could not tell you if there are clouds or not. That defines that this is beyond your visibility. So you can see the ridiculousness of trying to see something like the Rocky Mountains on a flat Earth from New York, just because the atmosphere doesn't allow for it. The atmosphere has all kind of things in it, mostly moisture, but it's also got sand and dust and debris. Always, guys, always. If it didn't, you would not have clouds. Little debris in the atmosphere is necessary for any kind of water droplets to condense in the air and form clouds. It's called microscopic nuclei. So for us to be able to see, in that case it would be 2,000 miles, that's total ridiculousness, just totally ridiculous. But in any case, let's get into this right here, the question. The question was, and if you see this video, you'll understand how he absolutely proves that a river running by his house proves that we live on a flat Earth. To me, it's one of the best proofs I've actually ever seen, guys, and I just saw this today. So let's get into this, because the actual question, let's get into the question first, and that'll describe the answer. Okay, hopefully this is readable to you guys. This user here said, can you please define downhill and why it's not that way on the globe? And the person, Awake Souls, who made the video said, downhill is a gradient that water will flow down. The entire video is about it and not that way on a globe. The questioner responds, right, but you still didn't answer the question. What is downhill? Meaning, what causes water to move downhill? Now I'm going to read my response here, and then I'm going to detail this. And this should forever answer the question, gravity or not gravity. And you can look at the evidence here and make up your own mind. But I think it's quite clear. I wrote, water runs downhill because of the nature of fluids to become level. Water is moving through a fluid on the Earth. That fluid is called air. And by the way, guys, I'm going to explain all of this. The air pushes water and everything else down with a force of nearly 15 pounds per square inch. We don't feel this pressure because our bodies are pressure negative. I should have written pressure neutral due to air inside and outside of our bodies. if air pressure is, say, 25 pounds psi, then at sea level it would actually be different because water would seek to be level with that fluid pressure upon it. This is really how a barometer works. It forces water up a tube, and that amount of water pushed up the tube is measured, and thus we know our air pressure. Water flows downhill because it is pushed by the air pressure above it downward until it reaches equilibrium between the two fluids. The two fluids are air and water. Thanks for asking the question. It is a good proof that gravity has nothing to do with the process. It is density within a fluid, in which fluids must reach equilibrium. Fluids must reach equilibrium or they will continue to try to move until they do, guys. That is one of the laws of the physics of fluids. He wrote back, Mr. Thrive and Survive, as interesting as all that sounds, what is creating that downward force? And we're going to get into that. Plus, what are you doing answering me anyway? You have me muted on your channel, and I think the guy here who posted his video can answer his own questions, unless you think he's incapable. Well, I think he's very capable as far as what he produced. I don't know if he's a weatherman or a weather scientist, which I am. And by the way, guys, I do have a degree in science. It's just not in physics. I do have a degree in one of the sciences, believe it or not. It cracks me up, some of the things that people just think I don't know, and then they just don't even offer their, the corrections, so to speak. And anyway, whether he's muted or not, like I said, I don't know. I don't remember him. I certainly could have muted him. I don't know what he might have said. And like I said, others could have done the same thing. Let's move on. Quickly again, before I get to the animations, everything you see here in the air and in the water itself, they are both fluids. The air that you cannot see that is above these leaves here, all the way up to the top of the atmosphere, and all of the liquid you see, they are both fluids. Just because you can't see it doesn't mean it's not there. And for those of you who want to do more study on this subject, because it gets much deeper than what I'm going to go into here, and there are many more factors that go into it. But here we have Galileo himself, Galileo Galilei, and he knew, I like how that sounds, Galilei. He knew all about this, okay? This is Torricelli. And then we have what's called fluid dynamics and Bernoulli's equation. This guy right here, Torricelli, I hope I'm pronouncing that right, he knew all about air being a fluid and the pressure it exerted, just like water exerting pressure. In fact, many people know of barometric pressure and barometers, and we're going to talk about that. This is the guy that invented it, guys, okay? This guy, Galileo, was influenced by all this. In any case, fluid dynamics, air fluid dynamics in particular, you can look up. There's a thing called Bernoulli's equation, things I had to know in my science field, and it talks about the viscosity of air and how it moves as a fluid and different things like that. So you can get into that and understand how, when you really understand air pressure and that air is a fluid, it really erases all chances of gravity really being true. So let's get on with it. Okay, this is going to be great, guys, because a lot of you are going to be able to actually teach your kids this stuff. I'm going to make it that simple. Everything we know of that exists, that is real and tangible, is made out of molecules, correct? Every piece of matter is made out of molecules. Air is also made out of molecules, and so is water. Water molecules are more densely packed than air molecules. That's why water will be underneath of air in nature in most cases. There are some cases where molecules of water are lighter than molecules of air. This is when you see clouds. That is the exception to the rule. As in many things in science, there are exceptions to the rule. So let's take a look, now that you know this. It's that simple. The more molecules you have packed into one area, the more dense something is. This on the left, this box on the left, would be considered more dense than the one on the right because more molecules are packed into the same space than the one on the right. Hopefully that makes sense. This is the formula, okay, for density. Now, mathematics in most cases cannot prove anything. Mathematics is usually to describe a phenomenon. Density equals, now what you can use this for is to prove or disprove if your density calculations are correct. For example, if you have something that sinks in water and you have it calculated that the density of that object is less than water, you can go back and find out with mathematics what is wrong with your formula, or what is wrong with one of your values. That's how you can prove something is right or wrong. But generally, math is used to describe a phenomenon only. A lot of people want to say just because mathematics is out there, that's proof of something. Like people have mathematics to show the analemma, but it doesn't prove how the analemma gets its curves and how the sun moves fast and slow. It's just a description of the line that's drawn out in a sine wave. Density, okay? P equals m over v, where P equals density, mass equals m over v volume. So volume is how big the box, all right? Mass is how many molecules are in the box. So if we made this box 5 times larger than the one on the right, guess what? The one on the right suddenly would be more dense. So go back to the formula and that will show you that as well. Now let's move on to this. Torricelli, who invented the barometer, first did it, I believe, with water, but it may have been mercury. They found out that one was better than the other. Again, with most of what I'm going to say to you here, there are some variables I'm not going to be including. For example, different air temperature will change this, how you measure air pressure. Okay, if you take a tube, all right, create a vacuum, or actually you fill that tube up with water, fill that tube up with water and keep the bottom sealed until you immerse it into a container filled with water. And what will happen is, or mercury or other liquids, but we're going to talk about water here because we're going to be talking about the atmosphere and regular water, groundwater. If you fill a tube up, and it should be more than 30 inches, guys, make it 32 inches. You can do this at home. Fill a tube up 32 inches high and cap off the end like you would cap off a straw. You know how you can hold water in a straw when you pull it out of a glass. Insert it into water and the liquid will fall out of the glass, the tube, but not all the way. It will only fall to about 30 inches. Why is that? The reason is when it gets to about 30 inches, it equalizes the pressure that is forced down on the air in the container. So the air pressure then actually holds 30 inches of pressure, so to speak, into the tube itself. This is a good way to show how air actually is a fluid pushing down on the liquid fluid you have in the container here. And we're going to get into what actually pushes the air down on the earth. We're going to get into that. It's not gravity. Okay? So this is very exaggerated because high pressure on the earth, generally you're not going to get more than about 32 inches of mercury. That's the standard reading is in mercury. And the lowest, maybe in a deep hurricane, you're going to get 27.9, 28 inches of mercury. But that's generally range there. Okay, what you're looking at here is an aneroid barometer. It's the same thing. It measures air pressure, but it doesn't require water to do it against. It has different moving parts of metal that expand and contract, much like a spring. You can see on this barometer, the lowest figure down here, if you can read this, I'm not sure if you can, is 28.5 inches. And the highest figure all the way over here is 31.5. And I can tell you, on any given day, chances are you're going to be somewhere between 29.5 and 30.5. And in fact, probably 320 days out of the year, you're going to be between these two. Unless you're normally where hurricanes are, or extreme nor'easters, like on the east coast of the United States, even they don't generally get below 29.5 inches of mercury. High pressure systems in Canada can get up to 31 inches of mercury and a little bit higher, but that's extremely rare and usually in the heart of winter, okay? But generally speaking, you're going to be in here. Right? If the barometer is going up, that means fair weather is coming. If it's going down, it means unsteady or bad weather is generally coming. That's why when you hear barometric pressure given, at least in the old days, they used to say the barometric pressure is 29.72 inches and rising. It's actually a little bit more important the direction it's heading than what the actual number is, unless you're looking for a hurricane. Then if you start getting down in the 29s, you realize something big is heading your way. Now what you're looking at here is just another fancy barometer. You have room air pressure, which is air pressure that's going to be everywhere unless your house is perfectly sealed, and hardly anybody's house is. You're going to get the outside air pressure. And then you have internal air pressure, which is inside this, which is sealed. Okay, and there's a way to measure the height of the liquid to tell what the air pressure is. This is just a fancy liquid barometer. Let's take a look at one more. This is another example. This is an actual mercury-filled liquid barometer instead of water. Of course, mercury and liquid, both water, are both influenced by temperature. So you do have to make a temperature correction for any type of liquid barometer, whereas for an aneroid barometer, you do not. Hg is the symbol for mercury. So this is a vessel filled with mercury. And barometric pressure is always given in inches of mercury, at least in the United States. However, in the universal system, it's given in millibars. Now I'm going to try to remember my standards. If I remember, 29.96 inches is considered one standard atmospheric pressure at sea level, which is also 14.7 pounds per square inch. And I want to say that is 1013.5 millibars. I might be 1 millibar off there, but that's very close to what the standards are around the world. So depending on what your country uses, I just gave it to you. So what does that mean? That means that 14.5 inches, 14.5 pounds of pressure for each square inch of your body is being affected by air that much. You don't notice it because internally the pressure is equalized in your body. Now, if you want to know the differences, in your ears are the most sensitive to pressure. Suddenly go up in an elevator or climb up into a mountain in a car where you're going relatively quick, change in atmospheric pressure, and your ears will tend to pop. Everybody's pretty much experienced that I'm talking to. That is a difference in atmospheric pressure. It proves to you that pressure is there. You can tell the difference. When you go into a pool, if you go too deep, or into the ocean you go too deep, your ears are the first thing to feel the pressure. In fact, your ears would probably explode. Your eardrums would probably explode before your body felt the pressure enough to make you get out of the water. It is a protection that is built in to human beings, and I wonder how that evolved. It didn't. God gave it to you. In any case, so hopefully I've explained how strong air pressure is. It can force liquid up into a tube. Okay guys, I need to reinforce this idea. Everything in nature, every piece of matter is made out of molecules. How densely packed those molecules are determines where that matter will end up in a fluid. And I'm going to keep it as simple as that, and we're going to build on some simple concepts and get to how it all works. Now, I'm sure many of you have seen this or something like this. We have a container that's got all kind of different liquids in it. We have lamp oil, rubbing alcohol, vegetable oil, water, dish soap, milk, maple syrup, corn syrup, and honey. And we have a bolt and a kernel of popcorn and a dye that's in there, a cherry tomato, some beads, a soda cap, a ping pong ball on top. And as you can see, the liquids themselves will separate out into their different density levels. Why do they do that? Because the more densely packed the molecules, the more in physics, if you go back to the air fluid dynamics we talked about. It is forced downward. That's all you need to know. The less dense materials, well, let's put it this way. Something introduced into a liquid or into a, actually better it's said, into a fluid will keep moving until it finds its density equivalent. Once it finds its density equivalent, it will stop moving. It is not gravity, as I will show. The cherry tomato, which is right here, you put it in, it will go through lamp oil. Why? Because the cherry tomato is more dense than lamp oil. The molecules packed into a certain area are more densely packed in a cherry tomato than in lamp oil. Likewise, rubbing alcohol, vegetable oil, and water. A cherry tomato will sink in water. However, when it gets to dish soap and water, it's just about equal. It is less dense than milk. Therefore, the cherry tomato will stop here. If it was gravity, there was no reason for this to stop going all the way down to the bottom, just like the bolt. Now, it didn't necessarily have to be a bolt. It could have been a little screw that was lighter, if you weighed it, than the cherry tomato. There's a difference between density and weight, guys. There's a difference between density and weight. That's a very important concept. And we're going to get into that too. The bolt fell to the bottom because it was more dense than the fluid around it. And we're going to see that the fluid dynamics of air work exactly the same way. This right here should tell you there's something wrong with gravity. Gravity should pull all of these objects to the bottom, correct? But they do not. And we have exceptions in nature. We have water, which people say gravity pulls that to the ground. Well, a cloud is made out of water, and it's also made out of sand or dust or some other salt, in many cases, hydroscopic nuclei, and that floats above water. Why? Because the water molecules in a cloud are less dense than that of, let's say, river water. Otherwise, why doesn't gravity pull that water down to the ground? It's because it's not gravity. We are proving that gravity is a fallacy. It wasn't thought through. The inventor of it himself said it should not be taken as a fact because it wasn't proven through, all the way through. He couldn't do it himself. But they want you, see, gravity answers a lot of magical things, like you not knowing you're upside down. And we're going to talk about that, maybe, we'll see. Let's continue. Now let's start from some of the more simple concepts and move on. What causes weather, or what causes air movement at all on the Earth? Now, of course, I state, Airy's failure states, that every science experiment that was ever performed on the Earth states that the Earth does not move. Science has never proved the Earth moves 1 inch. To the contrary, those of you who are new to this, look up Airy's failure, A-I-R-Y'(S), failure. People have claimed to have debunked that, but they have not. That's BS. Anyway, what causes movement of air? Since it should all settle out if it's a flat Earth, not moving and not move, correct? Well, what causes rivers to flow? They flow downhill, don't they? Until they get to the ocean, and then it seeks to be level. Well, remember, pretend we can see the air. Unequal heating of the Earth's surface causes movement of the air. And in reality, it causes all the weather on the Earth as well. If the entire Earth were equally heated, there would be no weather, guys. There would be no life because there would be no precipitation. There would be no cycle like this. Air heats up. Over here, it rises until when? Until the density of the air itself equalizes with its surroundings, and then it won't rise anymore. An example of this is a hot air balloon. You blow up a balloon with regular air in it. Just blow it up and set it here, and what will it do? Nothing. It might blow with the wind, but it isn't going to go up, drifting up into the atmosphere, at least not far at all. It might go up a little bit because the wind might drive it. But let's say it's a calm day and you blow up a balloon. It isn't going anywhere. But if you heat up the air into the balloon, we know it will rise because we just made the density of the air less. It defies gravity. We haven't changed anything with the air, did we? It still has 70-some% nitrogen, 20-some% oxygen, and a bunch of little different other gases in it. Correct? That's correct. So without doing anything at all to the air, we didn't burn it. All we did was make it a little bit warmer. We caused it to defy gravity. Then as it goes up, what does it do? It cools. When it cools, the molecules get closer and closer and closer again. As it continues to cool, what happens? It sinks back down, back to the earth where the process is repeated. Why does it heat more at the earth's surface? Well, that's because land heats faster than the air around it. Land heats faster than ocean water. However, land cools faster than ocean water. This is what produces what's called land and sea breezes for those of you who live near the water. Sun comes up in the morning, it heats the land, correct? And what happens is the air above the land rises and moves out to sea, and then the sea air comes in and takes over the vacated air at the surface. It's cooler, it moves in. The process is reversed. Our homes are built on this process as well. Our central air conditioning units are based on this process. Cold air comes out, it sinks to the bottom, it heats up again, goes towards the top, and etc. We get a cycle that moves. Now I got to tell you guys, this is the best diagram I've seen to show what I want to show, but it is technically incorrect. I'm not going to get into that. I cannot believe how they will put incorrect stuff out there and have nobody obviously check it. This is my science, guys. I know it. This is technically incorrect, but I won't get into it. It does describe what I needed to describe. What eventually happens is you have high pressure areas build, and the best way to do this, because I can't even find a picture, so I can't believe they don't picture it this way anymore. I'm going to have a better picture in a second, but high pressure, pretend there is a bowl sitting on top of the ground here. The air heaps up in like a bowl, and that produces high pressure. There's so much air that it pushes down more on the surface, forces air down, okay? Then air flows into a low pressure system. And just as a side note, I remember when I first talked about the theory, the electric universe theory or magnetic theory, that high pressure systems are formed by the movement of the sun and or moon through the equator, and it does. It matches it perfectly with what we see with sea currents, but that's a different story. However, people were commenting, you keep saying high pressure systems, but it's low pressure systems that you should be talking about that are formed near the equator, not highs. And I couldn't understand it because it didn't make any sense. Here's the bottom line, guys. You can have high pressure systems without a low pressure system. You cannot have a low pressure system without a high. And I won't get into that right now, the reason why. But what's funny is Wikipedia was talking about low pressure systems near the equator, which they don't even exist near the equator. It was wrong. But anyway, people were trying to say I was wrong or whatever, and I finally figured out from a link somebody sent me that my whole theory was wrong because it's low pressure systems near the equator, not highs. You can't have a low or a high at the equator, guys. You have what's called convergence and divergence there. That's a different story. In any case, you have to be 10 or 20 degrees away from the equator to get either. Picture this is a dome and this is a bowl. A bowl and then a dome. High pressure flows out and down to the low pressure. They've got this, even though they're showing the circulation as in the northern hemisphere, they've got it backwards. They just do. But anyway, again, less dense air produces low pressure systems. Less dense air rises, okay? Now this says it has to be moist. It doesn't have to be moist, guys. Okay, that's how clouds are formed. I guess that's what they're trying to show here. But anyway, air and by the way, warm and cold air rise at different rates as well. That's another thing that defies gravity. Moist air, okay, rises at a different rate than dry air. Did you know that? It also cools at a different rate than dry air. All these things, when you really understand it, just totally dismiss gravity. They just do. So this is how it happens. This is how you get weather on the Earth. But you have high and low pressure systems that are formed. Again, generally speaking, the whole engine is caused by unequal heating of the Earth by the sun. Now this picture shows it a little bit better. The higher pressure pushes down more on the Earth than low pressure. Guys, they're both pushing pressure down on the Earth. The low is just pushing less than the high. That's the only difference. And you see how this is pushing this out, how it goes out in a clockwise direction and counterclockwise into a low. This, okay, just imagine this as rivers. The air is trying to find equilibrium. That's why it's moving in rivers, so to speak, in lines. If you ever look at a weather map, there are what are called, I'm going to find one and put it on here. All right, this is a weather map that is depicting high and low pressure systems. These lines are called isobars. Iso means equal. Bar means air pressure. So every dot, there's little weather stations that connect the dots here. These are called isobars. Every place this line goes around, the barometers under that circle where it is on the Earth measure 1024 millibars there. Everywhere along this 16 line, 1016 millibars are on the barometer in the people's houses where this is. 1012, okay? And as you can see, the closer you get to a high, the higher the pressure. 1024 is the high. We would generally write 26 under this high, or 27, because that would be the pressure you most likely find right underneath where the high is located, to indicate how high that high is or how strong it is. Low pressure, as you can see, this one's got 992 here. You'd probably write 98 or 97 next to the low to indicate the lowest barometric pressure. It's not even over 1,000 millibars. But still, guys, the difference between 1024 and 992 millibars is not that much, really. It really isn't. But it is a difference, and I can tell you, if you have millibars like this over Wisconsin, you're probably at 40 or 50 knot sustained winds. The closer these lines get, the stronger the winds. It's like putting your finger over a hose. The same amount of air has to go through a smaller squeezed area here. It's river, it's air river is what you're looking at by these lines. The air is flowing in a river along these lines. I can tell you right here that the winds are northwest. Why? Because if you follow the isobars, that's the same direction the wind is. Again, picture a hose. It's got to flow through this hose, and if you pinch it off, it's going to flow through at a stronger rate. It's not really more going through, but you're forcing more out you're forcing it out under pressure, just like putting your finger over a hose. It's not more water, but it's water coming out through a smaller opening. You understand what I mean if you have a hose. So this is going to make sense hopefully when I tie it all together here. Now we're back to this again because I need to get this definitely in your heads, this, what should we call it, this dynamic of fluids, okay? Again, what is pushing the water up into this? Air pressure. Now if we kept sticking different tubes in here, okay, they would flow out. Let's use this as a better example, because let's just say this is the 30-inch level here. This is a 60-inch tube. All right, just use that scale. It would fall out to the current air pressure. All right, now let's say you had multiple tubes in here filled with water. You put it in here, it would eventually overflow, right? The pressure coming out would overflow it. It's the air pressure that would overflow it. air pressure has a lot of effect on water. People don't realize that. Now, let's say that you had a bunch of these definite in there and it was just perfectly level with the top. And you had a bunch of different tubes like this. Okay, let me see if I can represent that. Okay, guys, I'm taking the time to do this because if you know this, you're going to be a genius compared to people like Neil Tyson deGrasse. Because he, as a scientist, should be able to look at this and see the same thing, that you can have the proof. Proof. This is how you can prove things, guys. This is the scientific method. And thank you to the person who sent me the scientific method who shows that science shows nothing. I'm going to do a video on that, I believe. But this is a good example of it. We can use the scientific method. We can stick 4 of these tubes in water. And what we can do is we can wait until high pressure comes over the area. And all these tubes, what will happen? They'll start filling up higher and higher and higher with water as the high pressure pushes down, correct? What will happen to the water down here? It'll drain less and less and less, right? As these fill up. This is the source. This is the source of water. Okay? It would have to drain from here. Likewise, if high pressure comes and pushes the water, low pressure comes and these drop, then this container would go higher and higher and higher until what? It would overflow. And why would it overflow? Because water water's got a property. It's got to seek the lowest level area it can find. Why? We can define that why in relation to the atmosphere. Because the atmosphere is also a fluid. Water is in, just like there was soap water above regular water in the other picture, and there was milk under the water. They were different liquids seeking their level, okay, within the other liquids. Water does the same thing. It seeks its level, or its molecular level, if you want to use it that way, with air, its companion fluid that it is in. The entire Earth is covered with an atmosphere. It is a fluid. Water is contained within that atmosphere. Just like the milk in the density tube, water will fall, okay, in its regular liquid form. It will fall until it reaches its lowest level that it needs to get to be stable in its fluid around it that it's in, which is the air, the atmosphere. And I hope this shows that there. What you can't feel, the atmospheric pressure actually forces water down out of this tube when the pressure is lower. Okay, when the pressure is higher, the difference is you have more surface area over here. Okay, I can't show that perfectly. Imagine these, I can't do that, these two combined here. Okay, the surface area that's exposed, not in a vacuum. Okay, higher pressure will push down, which pushes it up in here. Likewise, low pressure or lower pressure will cause the water levels to drop here, and they have to rise here because water is seeking its level compared to the atmosphere around it. This is why rivers flow downhill, and I'll show that in a little bit more clear detail if you haven't gotten it already. Now, we have a tank of water here. This is a stone, a small stone. It weighs less than the wood. The wood floats and the stone does not. Why? Why? People would say gravity pulled the stone down, but why isn't gravity pulling the wood down? Now, there's a reason why the wood is on top of here and not floating up. That's because the atmospheric pressure, it's holding it here, guys. Wouldn't you agree that if for some reason we could keep lowering the pressure and get close to a vacuum, this would come out of the water and get sucked out? Okay, the only reason why it's half depressed in the water is because of the air pressure acting upon it. However, it is less dense than the water is. when it is at this point in the, let's just assume this is where it found its level. Because there is wood that'll sink because it's more dense. So what about this rock? The molecules are closer together. That's why it sinks through its fluid. This stays here on top. It's held in, not by gravity, but by the atmospheric pressure on it. Guarantee you can get a little paper boat and stick it on top. And if you took the pressure out, there's a guy I watched recently that has a vacuum chamber. Please try this experiment. Because what will happen is before the water gets sucked out, because it's more dense than the paper or piece of wood on top. Paper's made out of wood, right? Wood makes paper. The paper would come out first. All right. And the only reason it sits is not gravity, but because the density of the air is more dense than the paper that it sits on. The same thing would happen with the wood here. I hope people can see that without having to actually perform that experiment. We're seeing it right here. We're seeing it right here. But let's go on. Now, what if I took this piece of steel here, okay, and I put it on the water, okay? What will happen to the piece of steel? Let me see if I can make that more clear. Maybe I can't. Nah, sorry, I can't do it. But anyway, if we put this piece of steel here, let's make it a smaller piece of steel so it fits in the container. What's going to happen to the steel? It's going to sink all the way to the bottom, isn't it? That's correct. But let's try another experiment. Okay? And people will say gravity's pulling it to the bottom. Really? Okay, let's find out. Let's find out if we do this. Okay, what if I take another piece of steel and put it on top of it? Two pieces of steel. They'll sink to the bottom, or will they float? They're going to sink to the bottom is my prediction. What if we take another one? Let's say we're up to 5 pounds of steel now. And we put this up here. Okay, another one. Let's take another one and put it on top. Okay, we keep putting steel on top here. How many pieces of steel can we get to put on top to keep it floating? Well, most people would say none, because gravity is going to pull it all the way down. What if we had, I don't know, 140,000 tons of this? Well, you'd end up with this. You'd end up with an aircraft carrier, and that sure is staying on top of the water, isn't it? How come gravity's not pulling that to the bottom of the sea? You see, if you say this has nothing to do with density, either in the air or on the water, you're fooling yourselves. There's no scientific logic then for this right here. Now, because the molecules have been spread out enough, and the carrier may have enough trapped air which is less dense than the water under it, it floats on top. All right, little sidebar, but I had to put that in there because it just makes gravity look stupid. How come gravity can't pull this down to the ground? How come gravity can't make this sink to the bottom of the ocean? Isn't it pulling it towards the center of the earth? Steel can't float on water, but yet this can. You know, all things being equal with gravity, that little block of wood that we were looking at back here, where was it? Yeah, this block of wood right here, okay? You could get into the ocean and hold on to that and let that save your life. You wouldn't sink to the bottom if you couldn't swim. Hold on to this little block. Well, we know that's not true. However, if this was, let's say, the size of a 8-foot oak door, yeah, you could get on that just like it's a raft and float around on it, right? Because then it's compensating for your body's density. It has to do with density, not gravity. All right, now let's get to the crux and end of the matter here. Here we have how a river flows. You have a snowpack on top of a mountain, okay? And the water is going down, it keeps flowing down until it gets to the river, and it will keep flowing until it gets to sea level. And please watch the other video that I showed at the beginning of this, and I will put the link at the bottom. Let me make this a little larger here for you guys. Okay, that's a little better, I think. So, why is the water running downhill? It is not because of gravity, guys. It's because of atmospheric pressure pushing down on the more dense water, okay, forcing it, just like it forced it up in the tube, okay, or out of the tube, okay, to where it becomes level, all right? And then it won't flow anymore because it's equalized with the fluid around it, the air. When, let's just say this river's at sea level, it's not flowing, it's dead right here, dead movement. Then it is equal, it is at the bottom of the container, just like the bolt at the bottom of the container of the different liquids. If you start to remove sea level, air pressure, and this is an important thing to know too. Now I'm going to make the big point. Let's go back to the first picture. Now I know a lot of people are going to think this is silly, but this really makes the point. Remember how the pressure pushing down, okay, changed the level of the water in the basin, okay? That is how the atmosphere acts on rivers and how it acts on lakes and ocean and any water. It is why water is pushed to the lowest level. Okay? I hope that makes sense. It needs to be at equilibrium in the container, which is the atmosphere above it, just like the cherry tomato had to reach its equilibrium point. Okay, a river is not as, if it's above sea level. That's why sea level is determined by atmospheric pressure, believe it or not. If you took away half the Earth's atmosphere, the oceans would rise. And guess what? You'd have more land. If the atmospheric pressure were greatly increased, the sea level would overflow the land and you would have lower seas. Sea level is caused by 14.7 pounds per square inch of pressure pushing down on the liquid. When the water is above sea level, it has not reached its point in the container where it is at its equilibrium with the other liquid, or the other fluid I should say. At sea level, everything is at equilibrium with the atmosphere. When water is above sea level, it hasn't reached that part of its container yet. I hope that makes sense. Just like when we have hot air balloons, all right, we can have a balloon over here on the left and a balloon back there that's floating. What's the difference? They both have the same amount of air, but one's got hot air, all right? It floats, but the other one doesn't. Gravity doesn't account for this. Density does. We can have the one in the back have much more molecules than this front balloon. In fact, we could have a balloon just laying on the ground. But the back balloon be totally filled with helium and it will rise. Much more molecules than the balloon at the bottom. This is a problem for gravity, but not for density. Gravity has issues. Density does not. And if gravity has issues, it's not the method. It's not correct. Density, when you understand fluid dynamics, explains it all. Explains why that balloon can be back there with many more molecules than the front balloon and yet be above sea level. It's all density, folks. And the reason why water flows downhill is because the density of the air is pushing it downhill. It's not gravity pulling it towards the center of the earth. So I hope that explains everything in this video. Maybe I'll need to explain more, but I'll end it here. Thanks, guys. Take care. Gravity. It's been blown out of the water, literally. Take care.